Dear colleagues, we present a video of the model's operation demonstrating the key aspects of the proposed approach to reducing the amplitude of transverse vibration in rotating shaft-type elements. And this concept is founded upon creating an active mechatronic system for monitoring and actively counteracting the growth in the amplitude of transfer oscillations or vibrations of rotating elements within mechanism, particularly shafts. The initial stage of the project, which involved the design and manufacture of the model's body and the selection and purchase of the main structural elements of the control systems, was conducted in the University of Melbourne in collaboration with Professor Kevin Otto and his students. The second phase of the project, which entailed the design and fabrication of the remaining structural components of the model and its control system, in addition to their installation, testing and adjustment work, was undertaken by Anatoly Bula, a student at Lutsk National Technical University. This device is defined as a mechatronic system, given that it incorporates a microprocessor in conjunction with electronic, electrical and pneumatic, but in real a device should be hydraulic elements. It is capable of autonomous operation in that it can perform the main target function of the device, that is oscillation damping or vibration damping, without the need of access to a high-level control system. In other words, this device can be integrated as a discrete module into a more complex system containing rotating elements, yet it is capable of autonomously performing its primary function, like oscillation damping or vibration damping, without reference to a high-level control system. In essence, the high-level control system offers only basic directives about the initiation and the cessation or alternation of the device's operational moods. The device is capable of autonomous monitoring of the operational status of the rotating elements and its functional parameters, as well as the generation of an active influence to align the current parameters of functioning of the rotating elements within its normal values. The working version of the proposed oscillation damping system involves the use of liquid as a working medium for both the active monitoring system or signal system and the subsystem for active force influence on the position of the rotating element. In this model, for simplicity, air is used as a working medium. This imposes certain restrictions on the demonstration of the functioning parameters, but reflects the main qualitative characteristics and principles of the device in accordance with the proposed idea. Such a limitation is the low speed of registering the signal of pressure increase in the pneumatic lines of the signal subsystem. This is due to the high compressive capacity of air, the short duration of the pressure increase stage, and the insufficient capabilities of the pressure sensors, which were selected as the most affordable just for the purpose of demonstrating the principles of operation. As a result, this model can only be demonstrated at low rotational speed. The active control subsystem or monitoring subsystem consists of several, in this case 2 lines, into which the working medium, in this case air, but in the working model it should be liquid, is injected with a small calibrated stable pressure. Each of these lines supplies the working medium to the window on the inner cylindrical surface of the device body. Near each window, pressure sensors are placed, both calibrated according to the nominal pressure of the working medium and configured to detect changes in it. In this case, the subsystem for generating a force impulse to correct the position of the rotating elements is simulated by light diodes, which reflect the formation of signal by the control system to create a hydraulic impulse. The high-pressure hydraulic lines are connected to the corresponding windows on the inner cylindrical surface of the device body. The number of these windows corresponds to the number of windows of the signal system. These windows have a specific shape different from the windows of the signal system, which allows for better transmission of the power impulse to the surface of the rotating elements and also provides the possibility of forming a wedging effect under certain parameters of the working fluid supply. To build a working model, we consider the possibility of using a piezoelectric actuator to generate a hydraulic impulse. A fuel injection system with piezoelectric actuators is considered as one of the closest prototype in terms of technical essence. This system is used in several diesel engines of several leading companies in the world, which indicates a high level of reliability of its operation and the availability of a system for controlling operation parameters. And this system is characterized by extremely high operational speed and the ability to create high fluid pressure. The control system of this device is based on the Raspberry Pi 5 microcomputer. This system processed signals from the pressure sensors of the signal subsystem and the incremental encoder. As a result of calculations in accordance with a specially developed program, a signal is generated to create a force impulse, which in this case is displayed by the operation of a light diode. The parameters of the control system and the device as a whole can be monitored on a special monitor. The operation of the device can be described in the following steps. The functioning of the rotating element with parameters that do not require adjustment, that is in the absence of vibration. In this device is simulated by a gray disk that is symmetrical and its axis of rotation coincides with the axis of symmetry. The video shows that during rotation the gaps between the outer cylindrical functioning surface of the disk and the inner functional cylindrical surface of the device body are the same in all directions and do not change during its rotation. Such a state of the rotating element corresponds to the nominal functioning parameters and does not cause a corresponding reaction in the monitoring subsystem of the device. This is a constant active monitoring of the state of this element. This is reflected in the presence of a stable uniform pressure in the window of the monitoring subsystem and is indicated by its sensor signals. The corresponding current information about the system status can be seen on the monitor screen. When a rotating element is subjected to external disturbing influences in the form of various types of displacement forces or bending torques that may occur during transient processes of the mechanism operation, transverse vibration may occur. In this case, such a state of the rotating elements is simulated by using a wide disk with an eccentricity in the form of a displacement of its axis of rotation relative to the axis of its symmetry. Visually, this can be seen in the displacement of the gaps between the outer and inner cylindrical surfaces of the disk and the housing respectively. The rotation of such an external cylindrical surface causes a change in the degree of overlap of the window of the signaling system, monitoring system, which in this case are located on the vertical axis of symmetry of the device body. This causes a change in the pressure in the line of working medium, which is recorded by the sensors. In this case, the formation of the pools of increased pressure in the working medium is caused by two main factors, one of which is associated with the overlap of the window through which the working medium exists, which consequently causes an increase in pressure in the corresponding line of the working medium, while the second factor is associated with the effect of moving and pushing the working medium inside the window, towards the window, due to the formation of the certain wave of the working medium with increased pressure in front of the place of the greatest convergence of the outer and inner cylindrical surfaces. In the same time, opposite phenomena occur in the opposite window of this signal system due to the maximum opening of the window on the inner cylindrical surface of the device body, which facilitates the easiest possible exit of the working medium to the outside, and as a result, a decrease in pressure relative to its normal value in this line of working fluid. The simultaneous reading of these two signals, indicating an increase and decrease in pressure in opposite window of the signal system, makes it possible to unambiguously detect the position of the rotating element's eccentricity at a certain point in time. This position is recorded by the control system and subsequently monitored via incremental encoder signals. This makes it possible to identify the moment of approach of the maximum eccentricity value to the windows of the system of force impact on the surface of the rotating element. At this calculated moment, a force impact is exerted in the form of a working medium pressure pulse on the functional cylindrical surface of the rotating element. In this case, the moment of formation of such a pulse is indicated by the LED light signal. When the eccentricity condition is maintained, the effect of overlapping the signal system window is repeated on the opposite side. This also causes the control system to generate a signal to create a pressure pulse of the working medium at the required time, that is when the next window of the force system is most closely covered by the surface of rotating element. The formation of the force impact can also be carried out in at least two ways. The main method is to transmit a pressure pulse of the working medium carried by the hydraulic pulse generator to the surface of the rotating element. The other method provides assistance in the radial movement of the rotating element by applying the effect of wedging the cylindrical surface of the rotating element and the device body with the working fluid. In other words, the liquid is fed into a wedge-shaped zone that is formed in front of the point of maximum approach or maximum convergence of the outer and inner cylindrical surfaces. This provides the effect of the repulsion of these surfaces during their mutual movement. The wedging effect can be created by pre-injecting a certain volume of working fluid before the window is covered. At the same time, at the moment of maximum overlap of the window, the so-called water hammer is also provided, which creates the main force effect for holding the position of the rotating elements at which its axis of rotation coincides with its axis of symmetry. As already mentioned, the availability of not only theoretical development but also well practically tested operating system for the formation of high-pressure hydraulic pulses using piezoelectric elements in diesel engine injector makes it possible to form a package of hydraulic pulses with different pressures and volumes of fluid supply in different phases of the maximum coverage of the outer cylindrical surface of the rotating elements with the inner cylindrical surface of the housing. As already mentioned, in this model device, the signal of generating a hydraulic power pulse is displayed by a light diode signal. The above features of the presented model do not distort the level of its demonstrational capabilities, since it provides a reflection of all the qualitative characteristics of the device functioning in accordance with the developed approach to active vibration damping. If it's necessary to operate the device at very high frequencies, this can be achieved by shifting the formation of a power pulse from the nearest window of the force impact subsystem to the next one in the course of shaft rotation. In other words, this provides additional time during which the shaft makes a larger angle of rotation, which leads to the eccentricity passing over the next window of the hydraulic pulse impact formation system. Student Anatoly also developed a software product that provides the main aspects of the functioning of this type of mechatronic system in the Python programming environment. At the same time, he identified the disadvantages of using the Python environment, which is associated with low data processing speed. To solve this problem, Anatoly suggested using C++ environment. To build a working model of this device, additional design refinement is required with the involvement of specialists in the field of hydraulic system, machine dynamics, control systems, and information technology. The presented model allows us to identify many useful effects for further development of system of this type. Thus, in conclusion, it can be noted that the application of the proposed system contributes to solving a number of problems associated with vibrations of rotating elements caused by various reasons. Conditionally, these reasons can be divided into two main groups. First is achievement of critical resonant rotational speed, and second is the effect of external disturbing factors, such as attachment of other elements, the influence of cutting forces through the tool, etc. Good steady-state performance of rotating elements at subcritical per-resonant rotational frequencies is currently achieved by balancing them. Other cases require active control and influence in order to reduce the amplitude of oscillation to avoid destructive and harmful effects of their action. And this approach may become a prerequisite for implementing the concept of operation of mechanisms and machines at supercritical rotational frequencies. That is when acceleration and transitions through critical rotational speeds occur without a working load, for example without cutting during machining. This opens up the possibility of using a range of supercritical rotational frequencies for various types of machines and mechanisms. Operation at high rotational speeds provides a wide range of opportunities to improve both the quantitative and qualitative characteristics of machines and mechanisms containing rotating elements. In particular, an increase in rotational speed makes it possible to transmit more mechanical energy, that is, increase power mechanical energy transmission, without increasing the geometric parameters of rotating elements and replacing materials with more durable ones. In addition, the increased rotational speed, and in particular in the absence of vibration on the spindle, provides qualitatively new opportunities for machining, which is expressed in the provision of better surface quality and machining performance.